design, build, and test an automated weather balloon launch that is both reliable and functional, so it may be used to support SpaceX launch and test operations. The video you just saw was a test launch of the Falcon 9 rocket, performing a vertical takeoff and vertical landing maneuver. Wind speed data is one important parameter that the rocket's flight computer uses to achieve such a controlled ascent and descent. Therefore, within the industry, high-altitude weather balloons are often used to obtain meteorological data for this purpose. The subsystem that is in control of the release of the weather balloon is the launch control subsystem. This subsystem controls two major components: the holding clamps that keep the balloon and attached payload from rising, and bay doors that open and close to protect and shelter the balloon. However, weather balloons are traditionally released by hand, and this can create safety hazards for personnel involved in releasing a balloon so close to the time of launch. Therefore, the system will allow for the remote release of up to 3 weather balloons within a 1-hour window, as well as real-time tracking and logging of wind speed data as the balloon rises. The bay doors are located on top of the shelter and will slide horizontally to open and close. To do this, the doors will be linearly actuated by a threaded rod that takes the rotational motion of an electronic motor and turns it into a linear motion. The holding clamps are made of a material named Delrin and will open up upon launch command by the user to let the weather balloon and attached radiosonde sensor box rise upwards. The movement of the holding clamps is controlled by a solenoid that pulls the clamp back upon reception of a signal. The electromechanical systems used within the shelter are powered by power supplies that can be hooked up to any conventional 120 volts AC power outlet. Inside the weather balloon shelter, there is a beagle in black within a control box attached to various sensors, as shown within the red and yellow portions of the block diagram. This block diagram also shows the interconnections between all of the different subsystems of the proposed automated weather balloon launcher. Commands originate from the GUI in the top part of the diagram and then flow through the data and signal processing block until they reach the Beagle in black for the launch control system. From there, the Beagle in black processes the command signals, controls the electromechanical system to release the balloon, and relays the corresponding sensor data back to the GUI.
The instrumentation subsystem consists of multiple sensors that help verify the launch of the weather balloons. Additionally, it includes a safety feature similar to the ones being used for garage doors in residential homes. There are 3 different types of sensors that are hooked up to a local microcontroller: a force transducer, Hall effect sensor, and microswitch. The force transducer is responsible for detecting the presence or absence of the weather balloons. The Hall effect sensor determines whether the holding clamps are open or not. The microswitch detects successful bay door operation. The Hall effect sensor will be placed at the sides of the holding clamp with the magnet on the adjacent clamp. The force transducer will be attached to the bottom of the holding clamps to calculate the lifting force of the weather balloon. The microswitch will be attached at the point the bay doors are fully extended to keep the electromechanical system from pushing it any further. In order to ensure that the balloons have been launched successfully, control algorithms are used. This includes a script that anticipates the status of each sensor and acts accordingly to it. For example, if the bay doors are open, holding clamps are open, and there is no weather balloon present, then it can be assured that the weather balloon has been launched successfully. If one of these cases fail, then the reverse has happened, and a motor will actuate to carry on the desired operation. The main challenge for this subsystem is noise. Noise can provide a voltage offset that will produce adverse analog or digital outputs from the sensors onto the microcontroller. Additionally, restrictions from the microcontroller, such as voltage capacity in each pin, would have to be accounted for.
The tracking subsystem is responsible for receiving meteorological and GPS data from the weather balloon post-launch. This is accomplished by using a Yagi antenna, which will be pointing in the direction of the balloon throughout the balloon's travel. The main challenge of the system is having the antenna accurately follow the balloon. This will be accomplished by creating a structure which will rotate the antenna 360 degrees along the horizon and elevate up to 70 degrees from parallel with the horizon. The structure will implement various motors and a BeagleBone Black microcontroller to drive and control its automation. In this clip, there are 4 buttons, a BeagleBone microcontroller, and a basic 180-degree servo motor and its driver. The top and bottom buttons control the position of the motor, while the left and right buttons control the speed that the motor travels at. This is just a basic sample of the program that will ultimately be used to control the antenna. In this clip, the antenna is being used with the program seen before in order to elevate the antenna up to 70 degrees. Here the antenna paired with the receiver and modem is acquiring data packets from the radiosonde.
The networking and data processing subsystem consists of a single BeagleBow and Black microcontroller which is located inside of the balloon launch shelter. It is connected serially to the mechanical controller and communicates with the graphical user interface over Wi-Fi using Node.js and Socket.io. The networking and data processing subsystem is responsible for three things: continuously updating the GUI with launch shelter status information, transmitting control commands from the GUI to the mechanical controller, and informing the graphical user interface of controller status, potential problems, and errors. Here's a brief example of the basic server functions. First, I have my server set up and listening for connections on the right using PuTTY. On the left is a test GUI I made to emulate the real client. I hit begin test, which sends simulated controller data to the client, which can be seen as the values for each balloon change. For instance, these values change from good to fair, etc. Next, I will simulate what happens when a user tries to input a command in the GUI by running open bay doors. So, as you can see, open bay doors is immediately registered by the server, and now the server shows the current action being taken to complete the command. For instance, now it's opening the bay doors. If you look down here, bay door changes from closed to open, signifying that it worked. Currently, the server is very bare bones, only transmitting simulated controller data and only being able to process one command. The error handling is also very minimal. The remaining goals are to start sending real data from the mechanical controller by connecting it to the server, revamping the command processing, and providing a more complete error handling system.
The graphical user interface subsystem is programmed as a single-page application and uses the programming languages HTML, JavaScript, and CSS, in addition to frameworks and libraries such as Bootstrap, jQuery, and Socket.io.
The current core functionality of the interface includes displaying the launcher state data received from the server, alerting the user of system failures and warnings, providing controls for opening and closing a bay door, as well as launching a balloon, and finally, only allowing controls that are supported by the launcher state to be executed. For this demonstration, the launcher state was spoofed, and no connection to the server was actually made. In the next stage of development, the interface will be connected to the server using Socket.io to receive data and send control commands over the network. Upon loading the interface, users are first prompted to enter a password. If the password is correct, the core interface will present itself. At the moment, the only tab that is completed is the Launcher tab, which is responsible for displaying the launcher state and controls. If all the sensors are registered as good for a given balloon, the bay door controls are presented after hovering over the bay door box. For balloon 1, that is not the case since the first sensor is marked as bad. For balloon 2, the system state allows the bay door to be opened. After the bay door is opened, the corresponding balloon can now be launched. Once the balloon has successfully launched, the bay door for balloon 2 can then be closed by re-hovering over the bay door box again. Overall, the interface should always signify whether a user event is possible and allow users to perceive their stages of execution.